I will continue my discussion of universes, the sort of very powerful universes from a proof theoretic point of view that you get with inductive recursive definitions. So they are examples of induction recursion. I will then implement some models. I mean, first of all, model of system T. I think I mentioned earlier that system T is a very important precursor of type theory, intuitionistic type theory, invented by Gödel, actually in the 1940s, although the paper about it was published in 57 or 58. I will show how you can define the semantics of this system inside AGDA. And this is actually something which is very, very similar to what Amal was telling you yesterday about, types, proof of type safety for a language which is not exactly system T, but a language which is similar, in the sense that it was based on the simply typed lambda calculus and it had some recursive data types. What is particular about system T is that all programs terminate in a suitable sense. Another famous language that you should know about is PCF, which is kind of the general recursive version of system T. It's also just the simply typed lambda calculus with natural numbers and booleans if you wish, but which has a fixed point operator, so you can do general recursion. System T has only a primitive recursion operator, which I know many of you have exercised on in the AGDA exercises. So what I will do is very close to implementing stuff like similar to what Amal was showing on the board yesterday. I will then generalize it to type theory, showing how you can get the semantics of dependent types. And if I have time, I will say something about the semantics of equality. It becomes quite complicated then. And then I will finish up by discussing a little bit philosophically what is the philosophical status of this, how you can look at this as somehow the so-called meaning, Martin Löw's so-called meaning explanations, the sort of fundamental reasons why about what judgments in his systems mean and why the rules are correct. And and this is exactly the sort of thing which is considered to be the most advanced or convincing explanation of constructive mathematics. There are other approaches to constructive mathematics than type theory, like the set theory that I showed you, and there is also another tradition which is mainly associated with the American logician Pfefferman, and to some extent with Axel, where you instead have some kind of untyped language which you start with, and then you have a logic on top of that. But that can also be reduced to type theory. And type theory has this somehow very well discussed, maybe one should say, both from a technical point of view and from a philosophical point of view, discussion of these meanings. So I will finish with that. But I thought before I do all of that, I will just show you a feature of AGDA which you should know about, which is very basic and useful. Is that AGDA has records. So a record, is I'll write it here. So a record type is a type of tuples. So it's really tuples of arbitrary length. So you can say that it is, an iterated sigma type. mean, sigma type is, the type of pairs where the type of the second component can depend on the first component. I showed you before, the definition of sigma as a data. But there is another definition of sigma which doesn't use data, but which use record. Yeah, so one can say that in a sense, record are dual to data. Data is kind of, when you define a type by its constructors. You can see records as being defined by its destructures, the projections that you can take out the different components. So records should really be considered an extension of the logical framework. So it's on the same level as the dependent function space. So in Agda we write x colon a arrow b, right, for the dependent function space, often written with a pi, but in Agda it's written like that. We could, if the implementers of Agda so had wanted, they could have had a primitive pair type also on the level of the logical framework. And it could perhaps have been denoted by this notation, Rather than a sigma, one could say that, well, we used just as we used the arrow for also both for non-dependent and dependent function space, we could use the times symbol as a notation for dependent pairs. So, but Agda doesn't have that, but it could have had. But it has records. So the record notation is a little bit verbose, but don't let that discourage you from using it, because in many situations it is very appropriate. Yeah, by the way, I think Adam very quickly showed you that Coq has records as well, right? So does Agda. They work a little bit differently. Anyway, so let's look at the code. You see here that I have given an example of a parameterized module. This is just to explain the in the very simplest way, the syntax of records. So, I make a module called R, big R, in the directory record, which is parameterized on a set A1 and a family of sets A2, an element little a1 in big A1 and a little element little a2 in big A2 of A1. It's just so that I can build, some elements of this record. So here you see is the syntax of the record type. It's really sort of analogous to this thing. So what is, of course, characteristic of records is that you name the components. So x1 is the first component and x2 is the other component. Just like when you declare data, you declare record as, they have a type, they can have parameters. So the record will be an element of the type of sets. So recently they added a feature to Agda that you can declare a constructor. So if we want to have pointed brackets for these pairs, we can declare it like that. Agda actually lets you declare a constructor even without the pointed brackets, just underscore, comma, underscore, and then you can put in the parentheses yourself if you like the ordinary parentheses to denote pairs. So it's a little bit verbose, but it's quite a nice syntax, I think. So what do the elements look like then? Well, so now we declare an element, call it little r, and those elements are also denoted by the keyword record, but then we have, the different components should be enclosed in curly braces, and we say, that the first component, which was called x1, is a1, and the second component, x2, is called A2. So this is just a way of writing the pair A1, A2. And here we have used the constructor pointed brackets that we declared. So if you have a record, you will automatically get some kind of, user-friendly notation for the projections. So the first projections will be called big R, the name of the record type, .x1. And if you like, you can then define pi1 as another typical notation for that. Is R of x, R.x1. And similarly, you can define the second projection. It so happens, for good reason, just as this logical framework function space satisfies the eta rule, the rule that says that any function is equal to something beginning with lambda, so f is equal to lambda x fx. So in the same way, each record, each tuple is equal to some tuple notation. So even if it's a variable, you can expand it to a tuple. And we can actually test that this is the case by checking whether Agda can recognize that, okay, I'll just shrink it a little bit, that x is equal to pi, first projection of x, the pair of first projection of x, and the second projection of x. And it does. You can see that, yes, it says reflexivity. It means that when Agda type checks this, it will use the surjective pairing rule to identify those two things. They have the same normal form. When you define sigma with data, you don't get the surjective pairing. And this is also one of you observed, this is also the reason why the split Martin-Löw's eliminator for sigma is not definable in terms of the projections. With surjective pairing, it seems that it is. Do you have a question? Yeah, okay, good. Right. So I don't think I have time to dwell much on applications of records, but I just want to mention one thing which I think is quite cool. Namely that, so one use of record types and records is like sort of interfaces, like interfaces in Java or something like. You declare a number of operations which you have access to, and then you can have many different implementations, but the user really just looks at the interface. And this, of course, corresponds exactly to the notion of somehow algebraic structure in algebra. It's some operations satisfying some properties, and then you can have different instances of those. Like there, you can declare the type of monoid or the type of categories or the type of models of constructive set theory, and then you can instantiate them with particular implementations. So something which I think is quite nice is something which is very important is the theory of finite sets, or maybe we should call it the theory of finite subsets, because this is, of course, a major data structure for the world. Maybe even more important is the finite maps, because if you have a course in data structures, a lot of that course is different ways of implementing finite maps. And what is nice in Agda is, of course, that we can, on the one hand, declare the methods that work on that we want to have to work on finite sets, but we can also declare their properties. And it's actually quite nice, I don't know, it's not even an exercise, it's a project to try to define a nice interface for these finite sets. You could even be a bit pretentious and call it finite set theory. Right? And it's, of course, not quite unlike the set theory of Axel. It could have similar operations, although from a practical point of view, we tend to emphasize things like insertion and deletion of one element, and various things we can do. Still, the membership, the search, is perhaps the most fundamental one. So I won't go into details of this. I think it's a nice exercise, nice project to sort of work on this. I did something here about implementing this record in the most naive possible way as lists where we don't even remove duplicates. Yeah?
Why is the belong to set 1 universe?
Good question. So the reason here is that one of the components is a set itself. Yeah, so then you have to have a bigger universe in order to type it. Yeah, that's a good question. Thank you. Yeah, anyway, so you see I started implementing these operations for lists which are allowed to contain duplicates. Then you can do more and more advanced, and you can say you're not allowed to have duplicates, you can have sorted lists, you can have various kinds of trees, binary search trees, red-black trees, and so on, and of course the project gets bigger and bigger. Okay, so let's go from the useful to the useless. So let's go back to IR and the file higherinfinite.agda. So I started explaining how you build bigger and bigger universes. So we started with the first universe, and I told you that you could have a second universe, which is just like the first universe, but it has two new constructors, which somehow say that the first universe is a member of the second universe. And then both components of this universal Ataski are reflected in the second universe. Both the universe itself and its decoding function. So just as the original decoding function, big T, took a code for small sets and returned a set, now it returns an element in the second universe. Yeah, so someone asked me a question about the notion of small, and I somehow realized that maybe it was more confusing than helpful. It's some kind of terminology that's inherited from category theory, where you distinguish between small and large categories, and in order to do that, you need to distinguish between large and small sets. And there are two ways of formalizing that. Either this distinction is between a set and a class, for those of you who know a little bit of set theory, or the other way of formalizing it is the distinction between something which is an element of a Grothendieck universe and is a set in general. The Grothendieck universe is itself a set if you have an axiom stating the existence of an inaccessible cardinal. But the problem is that it's a little bit confusing that there are two uses of the word small. And similarly, when we discuss type theory, there is a similar double way of formalizing the idea of the difference between the small and the large. I told you about Agda's built-in universe hierarchy, set 0, set 1, set 2, etc. And this kind of a homemade universe hierarchy, U0, U1, U2, etc. So, but given that you know that there are these two ways of formalizing the distinction between small and large, I hope it's a helpful terminology. Then, of course, there are different level of smallness if we have different universes, but yeah, nevertheless. Okay, yeah, so the second universe, it's inductively recursively defined, so you have a decoding function which participates in the definition of the in the types of the constructors, just like in the first universe. So where I stopped last time was that I said that the passage from U0 to U1 and the corresponding passage from U1 to U2 and from U2 to U3 is uniform. It's sort of, you do exactly the same thing. You add a code for the previous universe. As a consequence, you can internalize it. And actually that's somehow a general comment about what happens when you kind of make things bigger, is that you have some process which is external to the formal system. And if you somehow internalize it, you tend to make something which is bigger. So here is the internalized version of the next universe construction. You think of big A and big B, the parameters of this definition, as being some universe UN Tn, and then you're going to build UN plus 1 and Tn plus 1. And you do that simply by adding constructors for UN and Tn in UN plus 1 and Tn plus 1. And then, just like all universes, they should be closed under all the basic type formulas, like pi is given here as an example. But you see that it's exactly the same as the definition of U1, except that it's parametric in the universe that you extend. So, but now you have an operation going from UN to UN plus 1, called next UN next T. Now we can make a universe which is closed under that. So we have to have, so now we build something which is called a super universe. It contains the first universe, but now the other UN, U1, U2, U3 are obtained by the next universe operators, which are now internalized, their operation inside the super universe. And yeah, so this becomes powerful. And of course you can do more things than just the infinite hierarchy, because now you can combine these with all the other type formers to build bigger and bigger things. So this is somehow much bigger than just the kind of limit of the sequence U0, U1, U2, etc. And one can, so when you do things like this, you should of course be careful so that you don't overstretch yourself. It could become inconsistent if you are not careful, because you are of course playing with strong things. But what do you do in order to know that you are not in trouble? Well, you can somehow proceed in two ways, which is what I will talk about later on. Either you prove that it's consistent relative to whatever theory you're used to working in, like set theory. And for this kind of thing, you need some set theory with some large cardinals in order to prove this consistent. But of course you want it more, you want something more than just being consistent relative to set theory. You want to say that, well, it's actually constructively valid in a certain sense, which we will explain later on. And then you somehow need to resort to the kind of thinking that I will explain later. And this is somehow accepted as a good constructive definition. I will not go through the kind of the nuts and bolts of how you reason in order to somehow convince yourself that yes, this must be correct. But you can. So this can be further generalized, and then you get something called a Marlow universe. This is also correspond to something called a Marlow cardinal, which is also a very old but very big cardinal. It is apparently not very big in the eyes of people working in set theory who have many even bigger cardinals, which are not, at least not yet, represented by analogs in type theory. But there are other things called, measurable cardinals and shrewd cardinals and compact cardinals and stuff like that. I believe this is an active part of set theory, which I don't know anything about myself. But Marlow cardinals can naturally be implemented in type theory. And the generalization is simply to say that we can make a universe not only closed under the next universe operator, but on any universe operator. On any pair f and g, think of them as, the next universe and next universe u and next universe t. But actually now we have no criterion on them. It can be an arbitrary mapping. This becomes even more general. It's easy to see, of course, that the super universe can be obtained as a special case of this. And what you do then, is that you have to have codes, just as you had codes for next universe and next universe decoding, you have codes inside the Marlow universe. And perhaps surprisingly, this is also, good constructive definition. So, I'm not really intending you to go in and think about this in detail unless you're specially interested in this particular direction. It's the sort of thing which is of great interest to proof theorists who try to classify different systems by how powerful induction principles they have. And they classify them in terms of ordinals. The ordinals, they represent, how much induction can you do in a certain system. Okay, so let's go from the supremely useless to something which is sort of useful. Well, it was useful because Amal talked about it yesterday, so someone else talked about it. So she thought it was useful. So I think it is, what is it? It's useful because it's a way of, it's just an example of a way of reasoning about the programming language, just as Amal's example was that. And it's somehow useful in order to understand the language, to analyze its semantics. And it's, very nice that you can do this so naturally in a system like Agda or Coq for that matter. Okay, so let's formalize this Gödel system T. So you see here that I have a new directory, semantics. I have file system T. It uses natural numbers and finite sets and vectors, where I have renamed the infix cons operation to cons, so that because I will use that for typing later. So we begin by defining the set of types of system T. It has function types and it has a base type natural numbers. So this is easy grammar of types. Then, we will, it's a lambda calculus, so in general we can have an arbitrary number of free variables, and they are typed in a context. A context is just, in this representation, it's just a list of types, because I use a nameless representation of variables, so-called de Bruijn indices, so that somehow the last declared variable is naught or x naught, and then x1, x2, etc. So it's an economical way of implementing lambda terms, although of course it results in less readable terms than if you have named variables. And we keep track of the length of the context. It's a vector of length n, vector of types of length n. And we declare it, the function arrow is always considered right associative, and we declare a precedence for it. So now, next thing to do is to declare the terms. And usually when you write a grammar of terms, you tend to put them all in one set, but it's nice to keep track of the maximal number of free variables allowed. So I call those the set of terms of Gödel system T, set of lambda terms with these extra constants, 0, successor, and the recursion combinator. I call them, the f of n, where n is the maximal number of free variables. I call it f in honor of Peter Axel because he used that symbol for it. You could call it term n if you like, a little bit more. You think of this as the type of n-place functions. Functions depending on at most n free variables. Yeah, so maybe I should just write the grammar here in the ordinary notation. So it's like writing, we have if I use the little a again for terms, then, we have var I for I being less than n. It's an element of the type fin n of, numbers less than n. Or it's application written in ordinary notation just by juxtaposition. I had to use the hash sign. It was only because there are the better signs are all reserved in Agda, so I'm not very happy about that, but I couldn't. If you have a suggestion for something which is better, then please let me know. You get used to it after a while, but of course initially it's not very intuitive. And then we have lambda, which is now without a variable, because it's with the Brown indices. And then we have, in ordinary notation, we have a 0, we have a successor, which is just a constant standing alone, and we have a recursor, a primitive recursor, like that. We could have alternatively defined successor as a unary function and a recursor as a ternary function, but we just declare them as constant because I want to generalize this to type theory, and I want to do something which is close to the logical framework that we have been basing Agda at. So I somehow want to show the semantics of a small fragment of Agda inside Agda. Okay, so now the next thing we can do is to define the notion of, the type system. And because of Agda's nice notation, we can have an infix ternary relation, gamma A belongs to big A, where we use the epsilon, the membership sign, to distinguish this object language belonging from the meta language colon. So you see here, for example, so it's a ternary relation, but it has one implicit argument, the number of free variables allowed here. So if we wanted to make that explicit, we could index this with n, for example, saying that context gamma has length n. Okay, so this is what the formal version of the rule for variables says. It says, that for any variable which is allowed, that is, it's a number less than n, it has the type of the ith component in the context. So we have a lookup function, which is defined, in the type of vectors, which looks up its type. So you see, in gamma. Is it too small, by the way? Should I enlarge it a little bit more? Is it okay? I've been on the back row, and I must say that sometimes, things look a little bit small on the board. At least for me, with my old eyes. Yeah. So the application rule. Well, it actually looks almost as nice as on a book page, right? If the function C has type A, internal type arrow B, and little a has type A, then C applied to A has type B, right? Easy pieces. The typing rule for lambdas is that if B, little b, has type big B, in the context gamma extended by A. So cons A gamma, will be the notation for gamma extended by A. What you would with variables be writing gamma comma x colon A, right? But we don't use variables, so we just use this nameless representation. So if you see that that's the way it looks, you will see also that it's correct that lambda of B will then be a term of type A arrow B in context gamma, because we discharge that assumption. And, well, sorry for sometimes being lazy, but I didn't write out the other typing rules for zero, successor, and recursor, so this is, exercise. Although, of course, the time of the AGDA exercise, this is finished, You can do it in your free time if you want to do something fun. The zero, the reason why I put a big F on zero, suc, and rec is because I have the ones without F, they are in the files that we defined before in the files of natural numbers. It's really worth it spending some time on having really nice notation. It could be better here. Okay, now folks, comes something exciting. And I don't mean the declaration of application as a left associative infix operator, but of course you know that application is always left associative, right? But it lets you write these in a nice way. So now, well, again, we do something similar to what Amal did yesterday. But here we do it because this is what Martin Löw did in 1979 when he made his big step and defined the meaning explanations. So basically what I'm doing is that I take what Martin Löw had in his 1979 paper, which was supposed to be informal justification of the theory, and I formalize it. And I begin with Gödel system T just to somehow do something which is, fairly familiar to you, especially after having followed Amal's lecture yesterday. It should be even more familiar to you. But you can see this is how Martin Löw would analyze the fundamental semantics of Gödel system T. So what was a little bit radical with Martin Löw's paper there, or Martin Löw's notion of computation, was that he had a lazy notion of canonical form. It's quite natural to have any first of all, so I should say this. I declare now a set of values. It could have been formalized as a predicate on the closed terms, the terms of type F0 without any free variables. So it's a formalization choice whether you have a separate set or whether you have a predicate. And this is, formalization choice that you are often faced with. It's often quite nice to have a separate set. In somehow categorical terminology, you would write something like this, that there is an injection map from the set of values to the set of closed terms, whereas the other one is, to have to have a predicate saying when something is a canonical form. It's just, someone means the same, but it's just two ways of formalizing it. What is nice about, yeah, well, I don't know, you could somehow do both, but what is good about this is that you can now do induction on canonical forms. You can sort of in the other way too, but anyway. Yeah, okay, so what are the values? The values are either an arbitrary closed term beginning with a lambda, so there must be, one free variable. There can be at most one free variable in the body. So I have to have a new name for the I don't actually even have to, because Agda actually lets me overload those. But I do. Lambda v means lambda in this as a canonical form. 0 is also a value. And then comes the radical thing. Successor of any term, even one which is not a value, is considered a canonical form. So this is actually somehow rather deep. It means that the whole type theory culture has been geared a little bit towards lazy evaluation. I can say that because Bob is not here yet. But often otherwise one would perhaps have a strict successor, so that there would be one. It should have a value as an argument as well. But it has somehow to do with the fact that we just observe one constructor at a time when we analyze the different constructs. It will also make it a bit more uniform, because you somehow treat successor as a constructor, or lambda as a constructor and successor as a constructor in the same way. I think that was also an argument for Martin Löw. Yeah, so I am sorry for being a bit lazy. So, I really should have defined the substitution function, which the special case of the substitution function where you substitute a closed term for a term with one free variable. But it takes a little bit of time, but it's it's sort of standard exercise that's also good exercise for you to do, especially with these indexed family, with sort of, it's not very difficult, but it's not entirely trivial. Okay, and now the computation rules, the way they were written by Martin Löw. It was also at the time, I think, a novelty. It became, later on known as big step semantics. Martin Löw did not call it that. It was also been called natural semantics by Gilles Kahn, a French computer scientist who promoted this. So Martin Löw gave what we nowadays call a big step semantics for this language. And this is sort of things like, so Adam wrote things like this, right? So this is big semantics for, so this is the beta rule written in big step semantics. In order to evaluate C applied to A, you evaluate C, and if it returns a lambda, then you take the body and you substitute the argument for it. And if that terminates with V, canonical form V, then the result of the application is V. So this is hopefully clear. In the case of lambda, anything beginning with a lambda has a canonical form, but it has to be in the type of value, so we have to sort of turn the lam into the lam V. And similarly for 0 is already canonical, so it's 0V. Successor, an application beginning with successor is already canonical, so it's of the form successor V of A. So you see here the successor of V is actually a unary operation, whereas suc F is a constant. Then you actually have in this, when you do this successor as a constant, you need to somehow eta expand it, because you want every function to be on lambda form. So the canonical form of successor standing alone is lambda x successor of x, but here written in the Brown notation. Yeah, recursion operator. Here's this, that is written in with big step semantics to evaluate rec of base case, step case, number. You evaluate the, we got first here up, number. If it's 0, then you evaluate the base case, and if it's v, you return v. And well, analysis the successor case, you call the recursion operator for, you know, the body of the successor, the predecessor of the number you started with. And also rec standing alone needs to be eta expanded. But this is the operational semantics, big step semantics for Gödel system T. So now we define what it means to be a natural number. So, you know, as a predicate of terms. So intuitively what it means is that this term has canonical form 0 or successor of something, where the something is also a natural number. So this is how Martin Löw defined natural numbers. So you see this is formalized here. If A evaluates to 0, then it's a natural number. And if A evaluates to successor of B, and B is a natural number, then A is a natural number. Clear, right? Now we define the typing relation on closed terms to start with. So this is a binary relation on terms, closed terms and types. And we say that, you know, to be a member of the type of natural numbers means to be a natural number. And then we have this clause, you know, which, you know, Amal was on the board drawn by Amal yesterday. To be a function from A to B is to be something that for any closed term A, which has argument type, when you apply the function to it, then you get the result type. And you know, this is somehow what is called a logical relation or a logical predicate. A logical relation or predicate is nothing but a relation defined by recursion on the type structure. And typically in a type system where you have function arrow. Yeah, so now you have done a large part of the job. In order to define types of open terms, we need to define a notion of environment. And you know, we have environment. It's a list of closed term, and we keep track of the length of the environment. And we have some constant or some relation which I call fits, which means that the closed terms in the environment have the correct types according to the context. Very natural, right? And this is defined in this obvious way that I won't elaborate on. And then we have a function which lets us instantiate a term with an environment, which I also have left as an exercise to define. Now we can define the notion of semantic typing. And because I have an implicit argument, I didn't quite know where to write that. In the definition, we need to use that implicit argument. I didn't know where to write it there, so I had to define an auxiliary constant, the only function of which is to be able to have somewhere to write the implicit argument, right? So it's a little bit silly, but if Agda allowed to write the argument in index position, it would be natural to put it there. But hopefully it's clear, So it just means that an open typing is correct if for an arbitrary fitting environment, the instance of the term in that environment has the right type. And then, you could go on and formally prove that this system is correct in the sense that if something is syntactically typable, then it's semantically typable. Yeah?
So from a multi-lecture row here was little gamma?
Let's see, so little, yeah, rho was little gamma, that's right, yes. Yeah. Yes, if we had really synchronized, we could actually have done things very close together. So I didn't know Amal was going to lecture about this, but of course it's nice when things come together. Okay, folks, are you ready for type theory? This guy we will kill. This guy we will look at. Yeah, so now the syntax becomes a little bit more complex because, in type theory, intuitionistic type theory, we evaluate both types and terms, and we have universal à la Russell, so we mix notations for terms and notations for types. So we have a few more clauses here for the types and for, yeah. So, before, it's exactly the same as before with variables applications, lambda, zero, successor, rec. But we have the types, which are now also terms, right? So first we have pi. So in ordinary notation, x colon a, arrow a. Here written with pi a and then a variable free version so that it's just pi a, but this one here binds a variable x. We have the type of sets, and we have the type of natural numbers. So this is the raw terms of Martin-Löw type theory, categorized according to the number of allowed free variables. We also need to extend the notion of canonical form, but it is completely systematic. We have to say what are canonical forms of pi form, set form, and nat form, the canonical types. And this is, what is initially a little bit unusual, that also the types have canonical forms. During type checking, you reduce the types so that they have canonical form. And the difference in type checking and what I'm showing you here is that type checking reduces open terms. But in the fundamental semantics, you consider the closed terms, the closed canonical forms. So you see, something beginning with a pi, something which is a dependent function arrow, is canonical, even if the types involved in it are not canonical. Set is, of course, a canonical type, and nat, take away the ugly spaces, and nat is, of course, a canonical type. And again, you can extend the substitution function on this extended set of terms. And now we have a big step semantics, which is, just an extension of the big step semantics we had before. Some cases for the type constructors. So for pi, it just says that if you begin with a pi, you are already canonical. If you are set, you are already canonical. And if you are not, you are already canonical. So that was easy. But note that in principle, you can build types with recursion here. So they can be non-canonical as raw terms. Yeah, that was that file. Now we will do the same for type theory as we did for Gödel system T. We will define the notion of typing. And we begin in the same way by saying what is a natural number in type theory. And it is the same. It would somehow be bad if the notion of natural number changed just because we go to the super theory of type theory. It should be the same, of course. And then comes the exciting thing, which is that when you generalize the notion of logical relation to dependent types, it's not only a recursion on the type structure, but it becomes an inductive recursive definition. So it's actually an inductive recursive relation or an inductive recursive family. So, when I drew the cube of inductive definitions, this is an example of something in the most powerful corner. It's both a family, it's inductive recursive, and it's actually generalized in the sense that the constructors have function type. Its character is close to a universe. It's sort of like a universe, but more complicated. But it's sort of similar to a universe. Right, so let's now look at this mutual inductive recursive definition. It's in the inherent character of an inductive recursive definition that it's a mutual definition of a data type and a function on that data type. So we always have to put the keyword mutual first and do some indentation of the definitions. So we now begin by defining, we define what it means to be a natural number. Now we define what it means to be a set. Then we will define what it means to be the more general notion of a type. So what is it to be a set? Well, intuitively, to be a set, it should either be a natural number or something obtained by previous sets by doing the pi type construction. So if we begin by the natural number case, anything which computes to the natural number type is a good set. In the pi case, if you want to, you can sort of read the definition in the following way. In order to know that big A is a set, you evaluate it. If it is a natural number, then you're done. If it's something of a pi type or a dependent function type, well, you're still not sure that it is a set because the argument type, big B, must also be a set. And the result type C must be a set for any x which is an element of the type B. And here comes the recursive part of the inductive recursive definition. We simultaneously have to define when something is an element of a set. So this is quantified over the closed terms x of type B. So simultaneously, we have to compute when a certain term, little a, of a certain type, big A, which is already known to be a correct set, is a set. Is the case. You think of this as a proposition. This is like a binary relation with an extra argument saying, that it's not even meaningful to ask if something is an element of a set if you don't know that it is a set in the first place. Because it's only if it's in a set in the first place that you know what to do to check whether something is an element of it. So let's begin with the easy case. If we knew that big A was a natural number set, because we can see this because the justification for it was this little nut set, which happened because big A evaluates to nut. Then, this, if big A is nut, then little a, then this, it's an element if this is a natural number. And in the case of when big A was a function type, B arrow C, and then you have to have arguments here where D is the proof that it had a canonical form of pi form, where little p is a proof that big B is a set, and Q is a proof that big C is a set for any X which is an element of B. If all of those, if you have all of those, then you can define, say that, well, and then we have a correct element if A applied to any X is of type big C of X, with the witness we have to, this is only meaningful if big C of X is proved to be a set, but we know that since we have the Q applied to X and Y. So it's a little bit involved, right? But if you take it very carefully step by step, you will see that it all makes perfect sense. It not only makes perfect sense, it's the absolutely canonical thing to do. And the intention by this is not that it is an arbitrary piece of complicated code, but it is actually the formalization of the fundamental meaning of this language. And it is supposed to represent the most satisfactory way of analyzing the semantics of this fundamental theory. So, look at this in awe. The next thing to do, final thing to do, is now to generalize and say when something is an arbitrary type. And the definition of being an arbitrary type is exactly like being a set. It's just that we have an extra case because this is like, a second universe which contains the first universe. So there is a new constructor for sets, but I won't elaborate this because I will say before my time runs out, I will say something like this. So I should just say, that here I haven't actually generalized this to hypothetical judgment. So this is also an exercise for someone who is keen to know more about this. I think it's, it's non-trivial exercise certainly, but interesting. Yeah, so let me just very quickly show that I have only here defined the typing judgment, but without going into detail, I can show the equality judgment, and in particular, it's interesting to extend the language with identity types. So, so I extend it with an identity type. Yeah, so this was the computation rules. I extend the language with an identity type and a constructor, usually called refl. It's happened to be ref here, but it means refl, reflexivity proof. And I extend, the computation rules with that, and then I can extend this definition. I will now define not only what it means for something to have a type, but for something to be, but for two elements to be equal elements of a certain type. And then when you work on this, something quite interesting happens, because you will realize that at some point you will actually need somehow heterogeneous equality. You need to have different types of the different elements. So this is meaningful only if those two types are equal. This is quite interesting. It's the sort of thing you discover when you try to formalize it. That I'm not absolutely sure that this is the only way of doing it, but it was the way that seems most elegant to do it. I tried to make do with only one of them, but I got into funny kind of things which didn't seem to work out, or at least seemed to work out in a more complicated way. But what I want to then say is that you can now define this, and you can define all of these meanings of this judgment of equal typings and so on, and you can do that for identity type, and then you will realize that you can justify the identity reflection rule. So you actually justify extensional type theory. So from this semantic point of view, extensional type theory is correct. Okay, so the last thing I want to say is to give you some kind of idea of the relation between, or why this is considered to be of such fundamental importance. Let's see now, so what should I do? I should do this. I should do... what do I do to turn off the... Yeah. I guess it will soon go off. Yeah.
I think you pressed no by accident.
Oh, I see, okay. Yeah, good. Okay, so let me just give you a little bit of a historical account of the development of intuitionistic logic and how this kind of, how one has looked at it. And I told you before that the founder of all of this was the Dutch mathematician Brouwer in the early years of the 20th century. And what happened was that he somehow made an analysis of logic which was completely revolutionary, which led him to the rejection of the rule of the law of excluded middle and the law of proof by contradiction. And the key point in his analysis was that he analyzed the notion of function as the notion of a method. So this was sort of pre-computers and pre-computation models. The computation models, they came in around, in the 1930s, like Turing machines, lambda calculus, recursive functions, etc. Gödel-Herbrand systems, the main ones. So he didn't have some kind of very precise notion of something being computable, but he had some informal idea that it should be something, effective to be done. So he also had this idea, that the proof of an implication is a method of proving, if you prove A implies B, then it's a method for transforming a proof of A to a proof of B. And for and to prove A and B is to prove A and prove B, etc. All this, which you go through when you explain the Curry-Howard isomorphism. And similarly, for universal quantifier, it's a method to turn an arbitrary element into a proof of a proposition for that element. So he had that informal idea, and those ideas were also elaborated on by Heiting, Brouwer's student, and Kolmogorov, the great Russian mathematician, who writes about this. What we should emphasize here is that when they did this analysis, they somehow did not work in some kind of particular precise mathematical framework. They used words from everyday language in order to somehow understand what's going on in mathematics. So they did not at all do the sort of thing that they built a mathematical model in order to prove that intuitionistic logic is consistent. They simply somehow tried to think about it, what is going on in mathematics. So much later, around 1950, another big name in the history of recursion theory, automata theory, and such things. Kleene, he had the idea that by using computation models, you could actually build somehow a mathematical counterpart of these foundational ideas using, the concept of a recursive function, of a Turing machine or something like that. So his idea, it was that, when you have a formula, let's call it, I don't know, phi, then you can realize it by, let's see now, it's good. So E realizes the formula phi. So E here is typically a number, and if this is an implication, then this should be a function. So, for example, it can be the index of a Turing machine or a recursive function when you formalize that. So in this way, he mathematically defined what it means to be a realizer of a certain formula. This is in fact a precursor to type theory, because this is much like a proof object. He didn't have the Curry-Howard isomorphism, he didn't design a type system, but he did something which is actually very similar to type theory, and it's especially similar to NuPerl, because NuPerl starts with an untyped language, and then the types are classifiers of untyped terms. So then, around 1970, we had these people like, I mentioned Howard in particular, de Bruijn, Scott, and ultimately Martin Löw, who somehow completed the search for a system based on the Curry-Howard isomorphism. Yeah, sorry, I should write it over here, actually. So in the beginning, when they somehow tried to justify their system, they had very informal justifications, but still justifications, certainly nothing like a model construction, except that Martin Löw, he had a normalization proof. Which, if you wish, can be considered as a model of normal forms, but they didn't quite express it like that. He just expressed it that every typable term has a normal form. So a few years later, Peter Axel again got very interested in Martin Löw type theory, and he did something very analogous to what Kleene did for intuitionistic logic. So here we have intuitionistic logic, and here we have intuitionistic type theory, ITT. Yeah. So he gave a model, much like Kleene's model, of the whole of intuitionistic type theory. This model goes under various names, like, for example, Frege structures. The main point about it is really that you start with some kind of untyped computation language. But in Axel's case, he had progressed, so his realizers were not numbers, but they were, terms in combinatory logic or lambda calculus. So, yeah. So this was, I think, 1974. So a few years later, Martin Löw came with his paper. In which he somehow tries to go back to the informal status of arguing about intuitionistic logic. Especially in his book, Intuitionistic Type Theory, published by Bibliopolis, this is particularly clear, where he says that, something like, what does logic mean or something? And he says, well, it could be interpreted as such symbolic logic, the analysis of, symbolic derivations or something, and foundational thoughts about the meaning of mathematics, or the mathematical analysis of logic. And he says that we shall do maybe the first, certainly the second, but certainly not the third. So it's certainly not about building models in a mathematical framework in order to justify his theory, but instead you should go back and analyze the primitive concepts. But what he does is discussing an untyped computation system and a notion of typing, which is completely analogous to what I showed you on the slide before. But the point is that if we call this step here as somehow formalization, the step of formalization of informal ideas in a mathematical language, we can take this step as somehow deformalization, or interpretation perhaps, where you take some formal ideas. I'm not sure that in either of these cases the arrows here are as direct as I make them seem, but in retrospect they seem kind of to go that way. So now you somehow take these mathematical definitions and you somehow ask yourselves, is this what my system means in some kind of basic so-called pre-mathematical sense? You distinguish between pre-mathematical when you discuss mathematics, trying to avoid as much as possible mathematical concepts, and meta-mathematical, or perhaps just mathematical, where you somehow analyze your theory given an already existing mathematical framework, usually set theory. So, so this is what you do. You can apply this already in the case of system T. You can somehow ask yourself, what was it that we were doing? Well, we were proving system T consistent in a version of type theory with some inductive families and so on. So we were proving it consistent in a much more complex and powerful system than the one we were analyzing. So actually, why should this give us any confidence that the system is correct? And indeed, the very first version of Martin Löw type theory with a type colon type, it was inconsistent, but Martin Löw had proved it consistent because he had made a normalization proof. The problem was that the normalization proof was itself in an inconsistent system. So it just shows very concretely how you can go wrong. So instead, you have to somehow think, what do they mean and are they really correct? And in the case of system T, well, it's sort of quite obvious. System T can be considered just as an ordinary programming language, very rudimentary, but nevertheless. That it is type correct simply means that when you sit in front of the computer and you run your programs, they will actually terminate. Of course, if you run Ackermann 777, you may have to wait a long time. But maybe you still have good confidence if you look at the intermediate results. Yes, we are on our good way. It may not happen before the sun burns out, but it seems to be going the right way, right? So this is why system T is correct. And we can somehow gain evidence by running various system T programs and see that, yes, actually it terminated. A function in system T terminates in the sense that each time you provide an input, it will actually return a correct output. And you can do the same game with Martin-Löf type theory. You can interpret all of what I did formally, somehow informally. What is a grammar? A child can understand how you generate terms from a grammar. You can take the definition of big step semantics and turn it into some kind of concrete procedure for actually computing the terms, which perhaps a bit bigger child could do. And you can see the different definitions of typing that I had as concrete recipes for how to check that a certain term has a certain type by computation. And you can do that concretely. You can accumulate evidence. And this is how you discover a counterexample, if there is one, or how you gain more and more confidence. That's my last word for today. Anyway, thank you very much all for listening. And again, thank you to the organizers who have, Jim, Zina, Bob, the others who in the organizing committee who have made this wonderful event. Thank you.